Introduction to word problems. In this video, we're going to give just a brief overview of the entire module, because this is a long module. Word problems are a large category of possible questions. Most of these can be solved with algebraic techniques. Some have numerical answer choices, and some have variable answer choices. As we will see, in addition to the straightforward way of solving, which involves algebra, we will also be able to determine the answer to the questions working from the answer choices first. So we have multiple ways of approaching these. The most common word problems fall into a few categories: age questions, motion questions, work questions, growth and decay questions, and mixture questions. Typically, these questions state the information in words and do not provide variables. We have to, first of all, assign variables and then write equations. So we need to talk about how to turn the words into symbols and equations, how to turn the words into algebra. We often have to consider whether to use one variable or more than one variable. This module will first explore the general strategies for all these problems, assigning variables, then writing equations. Then we will talk in detail about each kind of word problem, showing the straightforward algebraic approaches to how to solve them. And then finally, we'll have a few general videos on alternative problem-solving strategies, such as back-solving or picking numbers. So that is the basic layout of this module. To solve word problems algebraically, we need to introduce variables. The very first thing I will say is this: be thoughtful in the choice of letter for your variable. It's true that algebra, the math that we do, does not depend on the letter at all. Nevertheless, you will make your life easier and you will help yourself by choosing a meaningful letter. It will be helpful for you to choose a variable that, for example, begins with the same letter of the name of the person or thing for which it stands. Don't pick plain old X. This is a classic mistake that people make in word problems. They automatically pick X. And then what happens is, there are a bunch of variables in the problem. They pick X for one of them, they solve, and then they get X and they're wondering, all right, well, now I have this number. What is this number? Is this the answer, or do I have to use this to find the answer? So they don't know once they get the value what it is that they've found. That's why it's much more helpful to pick letters that would represent the different items and different people in the situation. Here's the beginning of a sample problem. I don't have the whole problem here, but here we have three women: Sarah, Mary, Helen. If I pick X for the salary of one of the women, I may correctly solve for it, but when I get that number for X, how will I know whether it answers the question? I'll get that X, then I might be wondering, now wait, did I just find Sarah's salary, or Mary's salary, or Helen's salary? For this question, S, M, and H would be much better variables for the weekly salaries of these three women. That way, if I find S, I know exactly what I found. That sort of thing. Other considerations in choosing a variable. Sometimes it can be helpful to assign a variable for the smallest value and then express everything in terms of that. Sometimes it can be helpful to assign a variable for the target value, what the question is asking. And the advantage of doing this is if you choose the target value as your variable, then as soon as you find the value, you're done. You've answered the question. Also, if all the quantities in the problem are related to a single quantity, if everything is expressed in terms of a single quantity, make this conceptually central quantity the variable, and then relate everything to that. Here's a practice problem. Pause the video and then we'll talk about this. Okay, at Greg's Groceries, a half-gallon container of organic milk costs $1.50 more than a half-gallon container of orange ice cream. Elliot bought 7 half-gallon containers of orange juice and 3 half-gallon containers of organic milk, spending $27 for all 10 containers. How much does a half-gallon container of milk cost? And so here, we're looking for milk. So first of all, I'm going to pick M for that. That's going to be that's my target value. In other words, if I find the value of M, I've answered the question. Now notice that the other variable, the price of juice, well, juice is $1.50 less than milk. Milk is more, so juice is less. So J equals M minus 1.5. And so everywhere where I would have a j, I can just substitute m minus 1.5, and I can write everything in terms of m. So the total price would be m, the price of milk, times 3, and then the price of juice times 7. And if we add up all those together, it should equal 27. So the price of juice times 7 plus the price of milk times 3 equals $27. So that's the single equation, and all we have to do now is solve that equation for m. We're going to distribute, and notice that part of that distributing, we're going to have to multiply 7 times 1.5. Let's think about this over on the side. 7 times 1.5, well, 1.5, I could write that as 1 plus 0.5. Well, 7 times 1 is 7. And 7 times 0.5, 7 times a half of 7 is 3.5. Well, now I just have to add those, and I get 10.5. So 7 times 1.5 is 10.5, so we can use that. So now let's distribute. We get 7m minus 10.5 plus 3m equals 27. Let's first combine the 7m plus the 3m, combine the like terms there. We get 10m minus 10.5 equals 27. Add 10.5 to both sides, and 27 plus 10.5 is 37.5. Now to solve for m, all we have to do is divide by 10. And of course, dividing by 10, we're just sliding the decimal place one place to the left. So m equals 3.75. Or in other words, a half-gallon container of organic milk costs $3.75. That's the answer. Here's another practice problem. Pause the video and then we'll talk about this. All right, so you might be tempted to use variables s, j, and p, but notice that everything is in terms of the fine. And so even though that's not the target value, it's going to make sense to pick one variable for the fine, because we can express what everyone paid in terms of the fine. So I'm going to pick f for the fine. Pick f for the fine, then we can express everything else in terms of that variable. So we're told that Joe paid $3 more than 1/4 of the fine. So f over 4 plus 3. Peter paid $3 less than 1/3 of the fine. So f over 3 minus 3. And then Sam paid half the fine, $4 less than half the fine. So that's f over 2 minus 4. And so all three of those shares should add up to the whole fine. In other words, if we add up this, this, and this, they should add up to f. So we'll just write that as a single equation. That's the equation for f. Just all the three contributions added add up to the whole fine. Well, first of all, the plus 3 and the minus 3, those cancel. So we have a lot of fractions here. And life would be much easier if we got rid of the fractions. So we should multiply by something that will allow us to clear the fractions. And this is, you may remember this from the lessons on fractions. If we multiply by the least common multiple of the denominators, the least common multiple of the denominators is 12. 12 is the lowest number that's divisible by 2 and by 3 and by 4. So we multiply every single term by 12. Well, 12 times f over 4 would give us 3f. 12 times f over 3 would give us 4f. 12 times f over 2 would give us 6f. And of course, 4 times 12 is 48. And then, of course, the f on the other side becomes 12f. I just add these. 3 plus 4 plus 6 equals 13. Add 48 to both sides. Subtract 12f from both sides. 13f minus 12f is just f. So f equals 48. So now we found the value of f. We have found the value of the fine. But that's not the answer. That's not what the question is asking. It's asking how much did Sam pay. Well, Sam paid half the fine. Well, half is 24. He paid $4 less than half the fine. Half is 24, so he paid $4 less. Sam paid $20. And incidentally, if you're curious, Joe paid $15 and Peter paid $13, and that's how they covered the fine. In summary, do not use genetic variables. Choose variables that will help you keep track of the numbers that in the problem. So the worst thing you can do is just pick X, because then you'll be wondering once you find X, what did I find? Sometimes it helps to choose the smallest value as the variable. Sometimes it helps to choose the target value as the variable. And if all the values are related to one quantity, choose that central quantity as the variable. Writing equations. Once we assign variables, we have to write an equation and solve. Many students can do the algebra once they have an equation, but getting the right equation can be tricky. I'll review some basics of translating from words to math. So some of this might be familiar already. The words is or are, the verbs in the text, correspond to the equal sign. So that's very important. It means as we're translating, when we get to is or are, that's where the equal sign is in the equation. If we have A is 50 more than B, so A is, that's A equals, and then this way of saying it, at least in English, 50 more than B, what we're saying is B plus 50. So it's a little bit backwards from the way we write it mathematically. We'd write B plus 50, but we say 50 more than B. So A equals B plus 50. If we had A is 50 less than B, well, this one also, it's backwards. 50 less than B, it means we start at B and go down by 50. So that's B minus 50. So A equals, A is 50 less than B, B minus 50. Suppose we have something like twice A is 100 less than 3 times B. Well, twice A, that would be 2 times A is. So 2 times A equals, that's the first part of the sentence. 3 times B, that's 3B, and then 100 less than 3B would be 3B minus 100. So that's how we translate it. Suppose we have A is 50% of B. So A is, A equals, 50% of B. Well, if we're finding a percent of something, we simply change that percent to a decimal and multiply. So that would be 0.5 times B. And notice that whole equation, A equals 0.5 times B, or A equals 1/2 B, we could just multiply both sides by 2. 2A equals B, and that would be the same information, but without any fractions or decimals. Now, by contrast, suppose we had A is 50% greater than B. Well, this is very different. This is not the same as the one before, and you may remember from our discussion way back in the percents and ratios and fraction module, 50% greater, that is a percent increase, and the multiplier for a percent increase is 1 plus the percent as a decimal. So 50% as a decimal is 0.5, 1.5 is the multiplier. So A equals 1.5B. We could also write that as 3/2 B, and so forth. Here's a practice problem. Pause the video, and then we'll talk about this. Okay. Alice and Bruce each bought a refrigerator, and the sum of their purchases was $900. Okay. So we use the very simple variables A and B for the price they spent. A plus B, the sum, equals 900. That's one equation. If twice of what Alice paid was $75 more than what Bruce paid, what did Alice pay for her refrigerator? So the first equation, the sum of their purchases is 900. Twice of what Alice paid, 2A equals 75 more than Bruce. B plus 75. So that second equation is 2A equals B plus 75. Well, we want to get what Alice paid, so what I'm going to do is I'm going to solve that first equation, the equation on the left, I'm going to solve that for B, so that when I plug that in to the second equation, I replace B, then I'll just get an equation with A. So I'll plug that in, then I'll add A to both sides. I get 3A equals 900 plus 75. I'm just going to leave it like that, not even add them up, because I have to divide by 3. Well, if I divide by 3, clearly 900 divided by 3 is 300. And 75 divided by 3 is 25, so it's just 300 plus 25, or 325. And that's what Alice paid for her refrigerator. Here's another practice problem. Pause the video and then we'll talk about this. Okay, in a certain company, 50% of Ed's salary is 20% of Ruth's salary. If the difference between their salaries is $90,000, what is Ruth's salary? Okay, so first of all, 50% of Ed's salary. So that we could write that as 0.5, or we could write that as 1/2 of Ed's salary is 20%. So that's 0.2 or 1/5 of Ruth's salary. So we can write this in terms of fractions. So half of Ed is 1/5 of Ruth. So notice, incidentally, what this means is that Ruth must have a much larger salary, because we can take only 1/5, a small part of her salary, and it equals half of Ed's salary. So Ruth is the bigger one. Ruth minus Ed is 90,000. Okay, so as in the last problem, we want to solve for Ruth. So it means one of the equations I'm going to solve for Ed's salary and then use that to plug into the other. And I'm going to choose to solve the left equation. I'm just going to multiply by 2. I'll get E equals 2/5 R, and then I can plug that in to the equation on the right. So I get R minus 2/5 R, and of course R minus 2/5 R is 3/5 R. You take away 2/5 of anything, you're left with 3/5 of it. 3/5 R equals 90,000. Divide both sides by 3. 1/5 is 30,000. Multiply by 5. R equals 150,000. And that must be Ruth's salary. Many times, writing the correct equation depends on the specifics of the problem. In the upcoming lessons, we will talk about several specific topics in word problems, and in those lessons, we will discuss typical equations for those topics. In summary, we talked about how to translate words into math. Those are very, very important skills to have mastered. Remember that you may have to do a certain amount of algebraic setup before you can write the equation you will solve. And as I said at the end, many topics have typical equations, which you will learn in the upcoming lessons on the different word problem topics. Number of variables. Some students have questions about how many variables to use in word problems. To some extent, this is not really a mathematical issue, but more a matter of preference. In other words, sometimes students get caught up on, well, is the right way to do it with just one variable or assigning 2 variables? And it turns out there is no absolute right way. You can do it both ways many times. It's really a matter of discerning what works best for you. So I'm going to show both methods, and it's very important that you, in your own practice both ways. If you solve a word problem with 2 variables, go back and solve the same problem again. Try it with only 1 variable. See what works best for you. And as you develop a sense of your own preferences, you'll be more comfortable with word problems. So here's a practice video. I'm going to say pause the video and solve this, and then we'll talk about this. Okay. This is a very simple word problem. Frank has $13 more than Glenda does, and together they have $81. How much does Frank have? So first of all, we're going to start approaching this just with 2 variables. The obvious choices are F and G. for Frank's money and Glenda's money. Frank has, so F equals 13 more than Glenda. F equals G plus 13. And then, of course, their sum is 81. Those are our two equations. Well, the equation on the left is solved for F right now. Technically, we want to solve for G because we want to eliminate G so that our final equation has F, because F is our target value here. So I solve for G, I substitute that in, now I have a single equation with F, my target value. Simplify, divide by 2, and we get F equals 47. That's how much Frank has. So that's one way to solve the problem. Let's think about this again using only one variable. Well, for the one variable, the smart variable would be our target value. Our target value is Frank. So we're going to use F. That's going to be our only variable. Frank has 13 more than Glenda. And so it means that Glenda has 13 less than Frank. So Glenda equals F minus 13. And so I'm going to use F minus 13 for Glenda. And then the sum of those two, Frank plus Glenda, F plus F minus 13, that equals 81. Well, this should look familiar. This is the same equation as we had before, so I'm not going to solve it again. It has the same answer. But this shows you whether you start with one variable or two variables, you really wind up in the same place. You may get there slightly faster if you use one variable instead of two variables, but then again, it can be hard sometimes to see how to set up everything in terms of one variable. So that's the trade-off. If you see that you can introduce just one variable and express everything easily in terms of that, then that might save you a couple steps and a little bit of time. Practice with this and experiment. If you find that when you pick only one variable you get confused or have trouble expressing the other quantities in terms of that one variable, then it might just work better for you always to start with two variables. So again, get out of the mindset that one way is right and one way is wrong. This is about finding your own preference, finding what works best for you. And if you find that one choice is more comfortable for you, is easier for you, then by all means go with that. What if there are more than two variables? Well, keep in mind that if we have n variables, we also need n equations to solve for those variables. We did have a lesson on solving 3 equations with 3 unknowns, so that's particularly tricky math, and that's typically more advanced than anything you'd need to do on a word problem. And forget about it for 4 equations or 5 equations. You just don't see that on the test. If a word problem talks about 3 or 4 items, chances are very good that we can relate everything to a single item, which will allow us to create a single equation. So here's a relatively simple word problem. So this is a little more simple than you'd see on the test typically. Pause the video and then we'll talk about this problem. Okay. Mark is 8 years older than Lisa and Peter's age is 3 years less than 3 times Lisa's age. If the sum of their ages is 80, what is Peter's age? So Mark equals 8 years older than Lisa. L plus 8. That's one equation. The other one a little trickier. Peter is, P equals 3 years less, so we're subtracting 3 times Lisa's age. So 3L minus 3. That's Peter's age. So notice we're expressing both of these in terms of L. Then the sum of the ages is 80. So we plug in those two top equations, we can just write one equation in terms of L. And so that's often what happens here. Even though we have 3 different quantities originally, we want to get it down very quickly to one equation with one variable. Now this one we just do a little cleaning up and simplifying. We get 5L plus 5 equals 80. 5L equals 75. So L equals 15. Now very good that we use sensible letters here. L equals 15. That's Lisa's age. That's not the answer to the question. We need Peter's age. So Peter's age, we have to take that, multiply by 3, and then subtract 3. Well, that would be 42, and that's the answer to the question. Now here's a word problem that is actually worthy of something you might see on the test. Pause the video and then we'll talk about this. Okay, Wendy left the house with $D in cash. She made the following purchases: gas for $3 less than 1/3 of D, a book for 1/6 of D, stationery for $6 more than 1/6 of D, groceries for 1/4 of D. After these 4 purchases, she had $4 left. What is the value of D? Well, very fortunately, they give us a variable, so we'll just stick with that variable, and everything is expressed in terms of that variable. So we can say D minus 3, that's the gas, plus 1/6 D, that's the book, plus 1/6 D plus 6, that's the stationery, plus 1/4 D, that's the groceries, plus the $4 left, all that together add up to D. So I'll do a little simplifying. 1/6 plus 1/6 is 1/3. And also neaten up the numbers. They just reduce to plus 7. Now I'm going to find a common denominator. Add all those fractions. I get 11/12 D plus 7 equals D. Subtract 11/12 D from both sides. I get 7 equals 1/12 D. Multiply by 12. D equals 7 times 12, or 84. And that's the answer. In summary, if there are 2 quantities in a word problem, it may save you time to use only one variable. And again, remember, this is very much a matter of personal choice. You need to experiment for yourself. Try it with 2 variables, try it with 1 variable, do that on several word problems, find out what works best for you, and then go with that. If there are 3 or more quantities in a word problem, you'll always want to relate all of them to a single variable and construct a single equation. Now we're done talking about general word problem strategies, and we can get into the particular question types. So the first question type we'll talk about are age questions. This category concerns people of different ages. What's tricky about these questions is that mathematical relationships can be specified at 2 different times. Right now, here's one relationship they have, and then so many years in the past or so many years in the future, here's another relationship they have. For example, right now Steve's age is half of Tom's age. In 8 years, twice Tom's age will be 5 more than 3 times Steve's age. How old is Tom right now? So what I'm going to say about this is the big mistake associated with this problem is thinking of the ages as a fixed number. People get very sloppy. They say, okay, well, S is Steve's age and T is Tom's age. Well, then that first equation, we can certainly say Steve's age is half of Tom's. S equals 1/2 T. We can say that. But for the second equation, we cannot just say, well, Tom's age will be 5 more than 3 times Steve's age. 2T equals 3S plus 5. We can't say that because in 8 years, the ages will be different. And we need to take that into account. It's not enough to say that T is Tom's age. We have to specify Tom's age when. So I'm going to say in most age problems, it usually makes sense to pick the variables to represent the age right now. Pick the age in the present moment. That usually is the best strategy. So for example, it's not that F is going to equal Frida's age. F is going to equal Frida's age right now. And then we use addition or subtraction to create expressions for ages at other times. So for example, F minus 5 would be Frida's age 5 years ago. F plus 7 would be Frida's age 7 years from now. We can create other ages based on the age now. We will use these expressions to create equations that correspond to statements about age relationships in the past or the future. So if we have in 7 years, Edgar will be twice as old as Frida, well, suppose we picked E as Edgar's age now, and F as Frida's age now. Well, in 7 years, Edgar will be E plus 7, and Frida will be F plus 7. So E plus 7 will be equals twice 2 times F plus 7. And that's our actual equation. So having seen that, think about this practice problem. You can pause the video and then we'll talk about this. Okay. Right now, Steve's age is half of Tom's age. In 8 years, twice Tom's age will be 5 more than 3 times Steve's age. How old is Tom right now? Well, first thing I'm going to say, T is going to be Tom's age now. S is going to be Steve's age now. And I could write it as S equals 1/2 T, but I think it makes more sense to write it as T equals 2S. That way I don't have to think about fractions. Now, for the other ages, I'm going to have to use T plus 8 and S plus 8. So twice Tom's age, 2 times T plus 8, will be equals 5 more than, so we're going to add 5, 3 times Steve's age. 3 times Steve's age is S plus 8. So we get this equation. 2 times T plus 8 equals 3 times S plus 8, and that quantity plus 5. Well, so that I don't have to worry about fractions at all, I'm just going to plug in for T. I realize that I'm not solving for my target value. I'll have to go back and find T later on, but that's fine because I can avoid fractions by doing it this way. So I just plug that in for T. Now I have an equation in S, multiply everything out, get everything all collected, and we get S equals 13. So that is Steve's age right now, and that's half of Tom's age, so Tom must be 26. In summary, age questions can be tricky when different mathematical relationships among the ages are specified at different times. And so we have to be very clear in defining the variables. It's not enough to say that F is Frank's age. We have to specify when. F is Frank's age now. We have to be very clear on that. Choose variables to represent the ages now, and then use addition or subtraction to create expressions for ages at other times.